Namaskar. In this video, we will study about extraction of metals. An ore contains a metal in the form of its compound with other elements. So, after the mining of the ore from the ground, it must be converted into pure metal. To obtain a metal from its ore is called the extraction of metal. The ores are converted into free metals by a number of steps which depend on the type of the ore used, nature of the impurities present and reactivity of the metal to be extracted. The various processes involved in the extraction of metals from their ores and refining are known as metallurgy. Please note that no single process can be used for the extraction of all the metals. The processes to be used varies from metal to metal. The three major steps involved in the extraction of a metal from its ore are: first, concentration of ore or enrichment of ore; second, conversion of concentrated ore into metal; and third, refining or purification of impure metal. We will now describe all these steps in detail one by one. Let us start with the concentration of ore. First, concentration of ore or enrichment of ore. Ore is an impure compound of a metal containing a large amount of sand and rocky material. The unwanted impurities like sand, rocky material, earthy particles, limestone, mica, etc. present in an ore are called gangue. Before extracting the metal from an ore, it is necessary to remove these impurities or gangue. The methods used for removing gangue from ore depend on some difference in the physical properties or chemical properties of the ore and gangue. By removing the gangue, we get a concentrated ore containing a much higher percentage of the metal. We will discuss the various methods of ore concentration in higher classes. Please note that the concentration of ore is also known as enrichment of ore. Second is conversion of concentrated ore into metal. For the purpose of extracting metals from the concentrated ores, we can group all the metals into following three categories. First, metal of high reactivity or highly reactive metals. Second, metals of medium reactivity or moderately reactive metals. Third, metals of low reactivity or less reactive metals. Different methods are used for extracting metals belonging to the previous three categories. Manganese metal, that is Mn, lies just above zinc, that is Zn, in the reactivity series. Manganese metal is obtained by the reduction of its oxide with aluminium powder and not carbon. This is because carbon is less reactive than manganese. Please note that carbon, that is C, which is a non-metal, is more reactive than zinc, and it can be placed just above zinc in the reactivity series. So, carbon can reduce the oxides of zinc and of all other metals below zinc to form metals. Another point to be noted is that tin metal, that is Sn, is more reactive than lead, that is Pb. So, its place is just above Pb in the reactivity series. Yet another point to be noted is that Copper can be extracted by the reduction of its oxide with carbon as well as by heating its sulfide ore in air. The extraction of a metal from its concentrated ore is essentially a process of reduction of a metal compound present in the ore. The method of reduction to be used depend on the reactivity of the metal to be extracted. This will become clear from this discussion. Extraction of highly reactive metals. The highly reactive metals such as potassium, sodium, calcium, magnesium and aluminium are placed high up in the reactivity series in its upper part. So, the extraction of highly reactive metal means the extraction of metals which are towards the top of the reactivity series. The oxides of highly reactive metals like potassium, sodium, calcium, magnesium and aluminium are very stable and cannot be reduced by the most common reducing agent carbon to obtain free metal. This is because these metals have more affinity or more attraction for oxygen than carbon. So, carbon is unable to remove oxygen from these metal oxides and hence cannot convert them into free metals. Thus, the highly reactive metals cannot be extracted by reducing their oxides with carbon. The highly reactive metals are extracted by the electrolytic reduction of their molten chlorides or oxides. Electrolytic reduction is brought about by passing electric current through the molten salt. This process is called electrolysis, which means splitting by electricity. Electrolytic reduction is brought about by passing electric current through the molten salt. This process is called electrolysis, which means splitting by electricity. So, we can also say that the highly reactive metal which are placed high up in the reactivity series are extracted by the electrolysis of their molten chlorides or oxides. During electrolysis, the negatively charged electrode, that is cathode, act as a powerful reducing agent by supplying electrons to reduce the metal ions into metal. During the electrolysis or electrolytic reduction of molten salt, the metals are always produced at the cathode or negative electrode. This is due to the fact that metal ions are always positively charged and get attached to the negatively charged electrode or cathode when electricity is passed through the molten metal salt, that is, molten salt means melted salt. Salts are melted by strong heating. The metals extracted by electrolysis method are very pure. They do not contain any impurities. First, when a molten metal chloride is electrolyzed by passing electric current, then pure metal is produced at the cathode, that is negative electrode, and chlorine gas is formed at the anode, that is positive electrode. Second, when a molten metal oxide is electrolyzed by passing electric current, then pure metal is produced at the cathode, that is negative electrode, whereas oxygen gas is formed at the anode, that is positive electrode. The highly reactive metals, that is potassium, sodium, calcium and magnesium, are extracted by the electrolysis of their molten chlorides, whereas aluminium metal is extracted by the electrolysis of its molten oxide. We will now describe the extraction of two very reactive metals, sodium and aluminium. First is the extraction of sodium metal. Sodium metal is extracted by the electrolytic reduction or electrolysis of molten sodium chloride. When electric current is passed through molten sodium chloride, it decomposes to form sodium metal and chlorine gas. The formation of sodium and chlorine by the electrolysis of molten sodium chloride can be explained as molten sodium chloride, that is NaCl, contains free sodium ions, that is Na+, and free chloride ions, that is Cl-. During the electrolysis of molten sodium chloride, the few reactions take place at the two electrodes. First, the positive sodium ion, that is Na+, are attracted to the cathode, that is negative electrode. The sodium ion takes the electron from the cathode and get reduced to form sodium atom or sodium metal. Thus, sodium metal is produced at the cathode or negative electrode. Second is the negative chloride ion, that is Cl-, are attracted to the anode, that is positive electrode. The chloride ions gives electrons to the anode and get oxidized to form chlorine gas. Please note that we cannot use an aqueous solution of sodium chloride to obtain sodium metal. This is because if we electrolyze an aqueous solution of sodium chloride, then as soon as sodium metal is produced at cathode, it will react with water present in the aqueous solution to form sodium hydroxide. So, electrolysis of an aqueous sodium chloride solution will produce sodium hydroxide and not sodium metal. Please note that just like sodium metal, potassium metal is produced by the electrolysis of molten potassium chloride, that is KCl. Calcium metal is obtained by the electrolysis of molten calcium chloride, that is CaCl2, and magnesium metal is extracted by the electrolysis of molten magnesium chloride, that is MgCl2. Next is the extraction of aluminium metal. Aluminium metal is extracted by the electrolytic reduction or electrolysis of molten aluminium oxide. When electric current is passed through molten aluminium oxide, it decomposes to form aluminium metal and oxygen gas. The formation of aluminium and oxygen by the electrolysis of molten aluminium oxide can be explained as molten aluminium oxide, that is Al2O3, contains free aluminium ions, that is Al3+, and free oxide ions, that is O2-. During the electrolysis of molten aluminium oxide, the few reactions take place at the two electrodes. First is the positively charged aluminium ion, that is Al3+, are attracted to the cathode, that is negative electrode. The aluminium ion accept electrons from the cathode and get reduced to form aluminium atom or aluminium metal. Second is the negatively charged oxide ions, that is O2-, are attracted to the anode or positive electrode. The oxide ions give electrons to the anode and get oxidized to form oxygen gas. Thus, oxygen gas is produced at the anode. Now, we will study the extraction of moderately reactive metal. The moderately reactive metal such as zinc, iron, tin and lead, etc. are placed in the middle of the reactivity series. So, the extraction of moderately reactive metal means the extraction of metals which are in the middle of the reactivity series. The moderately reactive metals which are in the middle of the reactivity series are extracted by the reduction of their oxides with carbon, aluminium, sodium or calcium. Some of the moderately reactive metal occur in nature as oxides, but other occur as their carbonate or sulfide ores. Now, it is easier to obtain metal from their oxides by reduction than from carbonates or sulfides. So, before reduction can be done, the ore must be converted into metal oxide, which can then be reduced. The concentrated ore can be converted into metal oxide by the process of calcination or roasting. The method to be used depends on the nature of the ore. The carbonate ore is converted into oxide by calcination, whereas a sulfide ore is converted into oxide by roasting. First is, calcination is the process in which a carbonate ore is heated strongly in the absence of air to convert it into metal oxide. For example, zinc occurs as zinc carbonate in calamine ore, that is ZnCO3. So, in order to extract zinc metal from zinc carbonate, this zinc carbonate should be first converted into zinc oxide. This is done by calcination. Thus, when calamine ore, that is zinc carbonate, is heated strongly in the absence of air, that is, when calamine is calcined, it decomposes to form zinc oxide and carbon dioxide. Thus, calcination converts zinc carbonate into zinc oxide. Second, roasting is a process in which a sulfide ore is strongly heated in the presence of air to convert it into metal oxide. For example, zinc occurs as a sulfide in zinc blende ore, that is ZnS. So, in order to extract zinc metal from zinc sulfide, this zinc sulfide has to be converted into zinc oxide first. This is done by roasting. When zinc blende ore, that is zinc sulfide, is strongly heated in air, that is roasted, it forms zinc oxide and sulfur dioxide. Thus, roasting converts zinc sulfide into zinc oxide. The metal oxides obtained by calcination or roasting of ores can be converted to the free metal by using reducing agent like carbon, aluminium, sodium or calcium. The reducing agent used depend on the chemical reactivity of the metal to be extracted. First, now we will see the reduction of the metal oxide with carbon. The oxides of comparatively less reactive metals like zinc, iron, nickel, tin, lead and copper are usually reduced by using carbon as the reducing agent. In the reduction of carbon, the metal oxide is mixed with carbon in the form of coke and heated in the furnace. Carbon reduced the metal oxide to free metal. Here is an example. Zinc metal is extracted by the reduction of its oxide with carbon or coke. Thus, when zinc oxide is heated with carbon, zinc metal is produced. Carbon is a cheap reducing agent, but it contaminates the metal. Iron metal is extracted from its oxide ore hematite, that is Fe2O3, by reduction with carbon in the form of coke. tin and lead metal are also extracted by the reduction of their oxide with carbon. Even the less reactive metal, copper, is extracted by the reduction of its oxide with carbon. Second, next we will see the reduction of metal oxide with aluminium. A more reactive metal like aluminium can also be used as a reducing agent in the extraction of metal from their oxides. Aluminium is used as a reducing agent in those cases where the metal oxide is of a comparatively more reactive metal than zinc, etc., which cannot be satisfactorily reduced by carbon. This is because a more reactive metal like aluminium can displace a comparatively less reactive metal from its metal oxide to give free metal. Thus, displacement reaction can also be used to reduce certain metal oxides into free metal. For example, the oxides of manganese and chromium metal are not satisfactorily reduced by carbon. So, manganese and chromium metals are extracted by the reduction of their oxides by aluminium powder. Aluminium powder reduces the metal oxides to metal and it itself oxidizes to aluminium oxide. We will now give the example of extraction of manganese metal by using aluminium as the reducing agent. Manganese metal is extracted by the reduction of its oxide with aluminium powder as the reducing agent. Thus, when manganese dioxide is heated with aluminium powder, then manganese metal is produced. This is a displacement reaction between MnO2 and Al, which is also an oxidation and reduction reaction. This example illustrates the use of a displacement reaction in the extraction of metals. The reduction of manganese dioxide with aluminium is a highly exothermic reaction. A lot of heat is evolved during the reduction of manganese dioxide with aluminium powder, because of which the manganese metal produced is in the molten state or liquid state. Please note that aluminium is an expensive reducing agent as compared to carbon, that is coke. From the previous discussion, we conclude that two reducing agents which are commonly used in the extraction of metals are: first, carbon in the form of coke, and second, aluminium powder. Now we will see what is thermite reaction. The reduction of a metal oxide to form a metal by using aluminium powder as a reducing agent is called a thermite reaction or thermite process. The reaction of a metal oxide with aluminium powder to produce metals are highly exothermic, in which a large amount of heat is evolved. In fact, the amount of heat evolved is so large that the metal are produced in the molten state. This property of reduction by aluminium is made use of in thermite welding for joining the broken piece of heavy iron object like grinders, railway tracks, etc. This is done as the mixture of iron 3 oxide and aluminium powder is ignited with a burning magnesium ribbon. Aluminium reduces iron oxide to produce iron metal with the evolution of lot of heat. Due to this heat, iron metal is produced in the molten state. The molten iron is then poured between the broken iron pieces to weld them or to join them. This process is called aluminothermy or thermite welding. Thus, thermite welding makes use of the reducing property of aluminium. After seeing extraction in reactive metal, we will now see the extraction of less reactive metal. The less reactive metals such as mercury and copper, etc., are placed quite low in the reactivity series. So, the extraction of less reactive metals means the extraction of metals which are quite low in the reactivity series. The less reactive metals which are quite low in the activity series are extracted by the reduction of their oxide by heat alone. For example, mercury and copper are less reactive metal which are placed quite low in the reactivity series. So, mercury and copper metals are extracted by the reduction of their oxides by heat alone. This is described here. First we will see the extraction of mercury. Mercury is a less reactive metal which is quite low in the activity series. Mercury metal can be extracted just by heating its sulfide ore in air. This happened as mercury metal is produced from the sulfide ore called cinnabar, that is HGS, which is actually mercury 2 sulfide. The extraction of mercury from cinnabar ore involves two steps. First, the concentrated mercury 2 sulfide ore is roasted in air when mercury 2 oxide is formed. Second, when this mercury 2 oxide is heated to about 300 degrees Celsius, it decomposes or get reduced to form mercury metal. Thus, here mercury metal has been produced by the reduction of mercury 2 oxide by heat alone. Please note that mercury 2 sulfide is also called mercuric sulfide and mercury 2 oxide is also known as mercuric oxide. Second, now we will see the extraction of copper. Copper is a less reactive metal which is quite low in the reactivity series. Copper metal can be extracted just by heating its sulfide ore in air. This happens as one of the ores from which copper metal is produced is copper glans, that is Cu2S, which is actually copper 1 sulfide. The extraction of copper from copper glans ore involves following two steps. First, the concentrated copper 1 sulfide ore, that is copper glans, is roasted in air when a part of copper 1 sulfide is oxidized to copper 1 oxide. Second, when a good amount of copper 1 sulfide has been converted into copper 1 oxide, then the supply of air for roasting is stopped. In the absence of air, copper 1 oxide formed here reacts with the remaining copper 1 sulfide to form copper metal and sulfur dioxide. The oxides of moderately reactive metals like chromium, manganese, zinc, iron, tin and lead, etc., which occur in the middle of the reactivity series cannot be reduced by heating alone. They need a reducing agent such as carbon or aluminium for their reduction to metal. Now, after extraction of metals, we will see refining of metals. The metals prepared by the various reduction processes usually contain some impurities, so they are impure. The process of purifying impure metal is called refining of metals. Thus, refining of metals means purification of metals. The method to be used for refining an impure metal depends on the nature of metal as well as on the nature of impurities present in it. Different refining methods are used for different metals. The most important and most widely used method for refining impure metal is electrolytic refining. Electrolytic refining means refining by electrolysis. Many metals like copper, zinc, tin, lead, chromium, nickel, silver and gold are refined electrolytically. For the refining of an impure metal by electrolysis, first, a thick block of an impure metal is made anode. It is connected to the positive terminal of the battery. Second, a thin strip of a pure metal is made cathode. It is connected to the negative terminal of the battery. Third, a water soluble salt of the metal to be refined is taken as electrolyte. On passing electric current, impure metal dissolves from the anode and goes into the electrolyte solution, and pure metal from the electrolyte deposit on the cathode. The soluble impurities present in the impure metal go into the solution, whereas the insoluble impurity settle down at the bottom of the anode as anode mud. We will now take an example to make the electrolytic refining of metal more clearly. Now, we will describe the refining of copper metal by this method. Electrolytic refining of copper. The apparatus used for the electrolytic refining of copper. The apparatus consists of an electrolytic tank containing acidified copper sulfate solution as electrolyte. A thick block of impure copper metal is made anode. It is connected to the positive terminal of the battery, and a thin strip of pure copper metal is made cathode. It is connected to the negative terminal of the battery. On passing electric current, impure copper from the anode dissolves and goes into copper sulfate solution, and pure copper from the copper sulfate solution deposits on cathode. Thus, pure copper metal is produced on the cathode. The soluble impurities go into the solution, whereas insoluble impurities collect below the anode as anode mud. Copper sulfate solution, that is CuSO4 solution, contain copper ions, that is Cu2+, and sulfate ions, that is SO4 2-. On passing the electric current through the copper sulfate solution, the few reactions take place at the two electrodes. First, the positively charged copper ions, that is Cu2+, from the copper sulfate solution go to the negative electrode, that is cathode, and by taking electrons from the cathode get reduced to copper atoms. These copper atoms get deposited on cathode, giving pure copper metal. Second is, copper atom of the impure anode lose 2 electrons each at anode and from copper ions, that is Cu2+, which go into the electrolyte solution. This requires less energy than the discharge of SO4 2- ion. In this way, copper ion are taken from the copper sulfate solution at the cathode and put into the solution at the anode. As the process go on, impure anode become thinner and thinner, whereas pure cathode become thicker and thicker. Thus, pure copper is obtained at the cathode. We will now discuss what happens to the metallic impurities present in the impure copper, that is crude copper, which is being refined. The metallic impurities present in impure copper can either be more reactive or less reactive. Now, the more reactive metal like iron present in impure copper pass into the electrolyte solution and remains there. On the other hand, the less reactive metals like gold and silver present in the impure copper collect at the bottom of the electrolytic cell below the anode in the form of anode mud. Gold and silver metals can be recovered from the anode mud. Thus, the electrolytic refining of metals serves two purposes. First, it refines or purifies the metal concerned. Second, it enables to recover other valuable metals like gold and silver present as impurity in the metal being refined. It is clear from the previous discussion on the extraction of metal that several steps are involved in the production of pure metal from their natural occurring ores. The summary of various steps involved in the extraction of pure metal from their ore are given here. Please note that if an ore gives carbon dioxide on heating or on treatment with a dilute acid, it will be a carbonate ore. On the other hand, if an ore gives sulfur dioxide on heating in air, then it will be a sulfide ore. Or if an ore gives hydrogen sulfide gas, that is H2S gas, on treatment with dilute acid, then also it will be an sulfide ore. In the next video, we will learn about corrosion. Namaskar.